Hello there, Mr. Sutton here, bringing you the Algebra 2 8-3 lesson on conditional probability. As the title suggests, in this one we are going to be finding conditional probabilities, and we'll get a little bit more into what that means exactly. We're going to begin this lesson with a definition of conditional probability. So here it is. The conditional probability, and here's this notation, this is the probability that B will happen given that A has already occurred. Probability that B will happen, and this vertical line is the given that part of this, given that A has already happened. So kind of a common situation where you might run into this is if maybe you're drawing cards out of a standard deck of cards, and you've already drawn a few, and you want to find the probability that your next card is going to be maybe a heart, given that you've already drawn 3 hearts out of that deck of cards. So this is very useful when things that you've done earlier have changed the possible outcomes of things you might do later. And because of this, you're going to be changing your total possible outcomes typically when you're dealing with conditional probability, and sometimes also the favorable outcomes. In that example we were just talking about, if you already drew some hearts out of the deck, then that's fewer hearts for you to draw on subsequent draws. Now, another place this might get used is if we want to kind of specify the limits of our sample space. So if you're rolling a 6-sided die, for example, normally the probability of rolling a 2 would be 1 out of 6. Favorable outcome would be one of those, and possible outcomes we have 6. But now let's say we want to talk about the probability of getting a 2 given that the number we roll is an even number. So if we're only considering even numbers and we just don't count anything that rolls an odd, well, in that case, there's only 3 even numbers to consider, and 2 is one of those, so that changes our probability to 1 out of 3. So we're changing our total possible outcomes to just the even numbers. So there's a good formula that we're going to be using quite a bit to sort of manage this conditional situation. The probability of B given A can be found by figuring out the probability of A and B happening, and just dividing that by the probability of A. We're going to use this in a bunch of different situations, but just want to unveil it now for you. For our opening problem here, we're going to talk about finding conditional probability using sample space. So let's say we have a family with 2 dogs and 2 cats, and isn't that cute? They randomly select a pet to get brushed, and then randomly select a different pet to get a treat. We want to find the probability they select a cat to get a treat, given that they've already selected a dog to get brushed. So one way to do these problems is to write out the sample space and just use that to figure out our probabilities. Now once you've got your whole sample space, all the different combinations written out, only the outcomes with the correct initial condition, first condition, which is that they picked a dog first, are going to count toward our favorable and the total possible outcomes. So with that said, pause the video and see if you can write out that sample space and figure out the probability based off of that. All right, so let's start writing out that sample space. I'm going to denote my pets as C1, C2, and D1 and D2, just to tell the difference between the cats and the dogs. So we've got the probability that we picked a cat first and second, so for brushing and for also for getting a treat. And I think brushing is actually the first one there. So, and then we have the probability that we picked cat 1 to get brushed and dog 1 to get a treat, and then cat 1 and dog 2. Now we've also got the possibility of picking cat 2 followed by cat 1, and then C2D1 and C2D2. And then we've got the probability of picking dog 1 first for all of those things. So dog 1, cat 1, dog 1, cat 2, and dog 1, dog 2. And then finally, the possibility, the events where we pick the second dog to get the brushing first. So dog 2, cat 1, dog 2, cat 2, and dog 2, dog 1. Now, we're given that we selected a dog to get brushed. We're kind of starting with that assumption. So we can only pick from these D1s and D2s where we had a dog get brushed first. So I'm going to limit my consideration to just these possibilities. And now we wanted the probability of a cat being given a treat. So we only want the ones out of this where we had a C as the second letter. So we have these two right here and also these two right here. So then our probability of selecting a cat given that a dog has already been brushed, probability of cat given dog, is going to be 4. There's 4 total where we get the favorable outcome, divided by, there's only 6 things we were considering. So 4 over 6. And then we can reduce that to 2/3. So writing out the sample space and using that works when you don't have a huge sample space, but sometimes you have very high frequencies of different things happening, and they're organized in one of these two-way tables, and we still might like to figure out some conditional probabilities. So on this one, we have a quality control inspector or inspecting team here, checking for defective parts, and here is the results in this two-way table. So we have parts that passed the inspection but were defective, parts that failed the inspection and were defective, and then we also had passes and fails that were not defective listed in this table. So in the first problem here, they're asking for the probability that a part will pass inspection given that it's one of the defective parts. So the idea here is we basically have to take a single item in this table and divide it by an entire row or column. And that'll give us our conditional probability. So we're not considering all of these results at once. We're just considering a single row or column when we're doing this. And what we're doing here also, this is going to work, this process, whether you have the original frequencies like we do in this table, or if those have already been converted into relative frequencies like you might see on some of the homework problems. Either way, this general process is going to work. So pause the video and see if you can figure out passing given that something's defective, and we'll bring it back together. All right, so if I want this probability, I need to find the probability, I need to find the number of things that passed and were defective and divide that by the total number of defective parts. So pass and defective divided by defective. So the pass and defective is this single entry right here, 3. And we're dividing that by all the defective parts, which is this whole row, the defective row. So 3 plus 36. And now we just have to plug that into the calculator. So here's my calculator. Let me make a little fraction here. We've got 3 divided by 3 plus 36. And that comes out to about 0.077. All right. So it's about a 7.7% chance that a defective part will actually pass. Now they also want us to find the probability that a non-defective part will fail, that it will fail given that it's one of the non-defective parts. Same kind of idea, just looking at things a different way. So pause the video and try this one out. All right, so just like before, we're going to figure out the number of things that meet both of these conditions, and then we're going to divide by the given condition right here. So we want to find the number that failed and were non-defective and divide that by the total number of non-defective parts. So fail and non-defective is this 11 right here, and we're dividing that by the total non-defectives, so 450 plus 11. And let's go to the calculator for that. So we've got, let's see, up here instead of 3, I've got 11. Down here I've got 450 plus 11. And that grand total is about 0.024. So pretty low chance, 2.4% chance that a non-defective piece will fail. For this next problem, we don't have a table. Instead, we just have kind of a word problem sort of setup here. At a school, we have 60% of students buying school lunch, 18% are just buying dessert, and then 10% of the students buy both a lunch and a dessert like we see on this plate right here. So we want the probability that a student who buys lunch also buys dessert. So this is a conditional probability setup. We're basically saying, given that you're buying lunch, what's the probability you will buy dessert? So for problems like this, it's helpful to define P of A P of B and P of A and B, basically all the pieces of the conditional formula, and then use the conditional formula to figure out whichever, A versus A given B or B given A that you want. So with that in mind, let's define these, and then you can go to work and actually use the formula. So P of A, let's let A be buying school lunch. So that'll be event A. They bought lunch. Let's say that B is buying dessert. And then that means that, P of A and B is the probability that they bought both. With things defined like this, pause the video and see if you can use that formula to figure out this part A right here. All right, so defining things, if A is the buying of lunch, P of A is going to be 0.6, 60%. P of B, the dessert one, is going to be the 0.18 right here. And then P of A and B, which we're going to need for our formula, is going to be this 10%, so 0.1. And we're asking for buying dessert given that we bought lunch. So basically we're looking for the probability of B given A. So the order is kind of important here. So this means we are going to want the probability of A and B, and that would be the same either way, divided by the probability of A, since that's what we're given. So in this case, we're going to end up with 0.1 divided by 0.6, which is just 1 over 6, or if we want to run those numbers on the calculator, 0.1 divided by 0.6 ends up being about 0.167. All right, so that's the basic idea. Pause the video and try this next one where we want to know the probability that a student who buys dessert also buys lunch. So now we're given dessert, so it's the exact reverse of the situation up here. All right, so let's see how that worked out. Now we're looking for P of A given B, given that we bought dessert. So we're still going to have P of A and B. That doesn't change. But now we're dividing by P of B because we're given the other event here. So this time we're doing 0.1 divided by 0.18. And that, if we plug that into the calculator, I'm just going to change this 0.6 to a 0.18. That comes out to about 0.556. So there we have it. So we have that a student who bought dessert is much more likely to buy lunch than the other way around, that a student who bought lunch is likely to buy dessert. So with this problem, if you are taking the CP non-honors version of the course, this is the end of the lesson. So you can turn off the video if you want, maybe go have that school lunch and try out some problems. If you're doing the honors, we got one more problem for you. So now that we did a problem on food, we have to do a problem on burning it off, right? So we have a jogger wanting to burn a certain number of calories during her workout. She maps out 3 possible jogging routes, and then before each workout randomly picks a route. Afterwards, she uses a fitness tracker to figure out if she reached her goal or not, and puts all that in this table here. We want to know which route she should use from now on. So we can't just look at whether or not she reached her goal, right? Because this isn't the whole picture. We also have to consider how many attempts she had on each of these routes, because if you attempted way more on one route than the others, then the fact that you met your goal a lot more on that route may not actually mean it's the best route for you. So we need the conditional probability in this situation that she met her goal given that she used a certain route. So what we're going to be doing on here is finding and comparing the conditional probabilities of reaching the goal on each route. So with that framework in mind, pause the video and see if you can figure out the best route for her. All right, so we're going to start with route A. So we're going to find the probability of reaching the goal given that we're only considering route A. So that's going to be the probability of reaching and A divided by just A. So that's going to be 11 here, 11 tally marks, divided by the whole row here for A, 11 plus 6. And let's plug that in the calculator. So we've got a fraction, 11 over 11 plus 6, which comes out to about 0.647. All right, so about 64.7% of the time on A. Can we do better? Let's try B. So probability of reaching the goal given that we're going on route B. So that's going to be reaching and B divided by B. So reaching and B is this 11 right here. And the whole row B is 11 plus 4. Let's plug that in. So we just have 11 still over 11 plus 4. The 11 was the same number of times reaching the goal in each of these routes. This time around, though, we had a 0.733 conditional chance on route B. So even though we had the same number of times reaching the goal, it turns out B had a better percentage. And now let's take a look at probability of reaching given that we're doing route C. So that's reaching and C divided by the number of C tally marks. So in this case, we've got 12, that's the most out of any of these, divided by 12 plus 6. And let's plug that in. So 12 over 12 plus 6 comes out to 0.667, which is interesting. Even though she reached her goal the most times on route C, it turns out when you actually factor in all the times she went on route C, the percentage was not the best. It was better than route A, but route B, it turns out, had the best percentage. So we will recommend that she use route B. So that is it for this one. Looks like I got to run. Till next time, Mr. Sutton, signing off.